with isomers or practice drawing isomers. And we're going to just stick with hydrocarbons in this example. So here we go. Here is our molecular formula, C6H14. So the thing you want to notice is that the H's ratio to the carbon, it's a 2N plus 2 ratio, which means that this is an alkane. And so our PCs in any of these will only have single bonds, and that is important, only single bonds. So I like to do these systematically. So I'm going to start with my simplest, which will be a 6-carbon chain. 1, 2, 3, 4, 5, 6, and I link them only together with single bonds. And this is the only one that I will actually draw in all of the hydrogens. So I'm up to 5, 7, 9, 11, 12, 13, 14. So since this one is just a simple straight chain hydrocarbon, this is just simply hexane. So if you have to draw two, if you were given a test question that says draw 2 isomers for this molecular formula, draw the simplest one first, especially if it's just a hydrocarbon, the longest straight chain possibility. To get to a next possible isomer is you change the PC size. So change the PC size. Decrease it by 1. So now instead of having 6 carbons in the PC, now I'm going to only do 5. And when you bought my molecular formula, it's an isomer, so it has to say have the same molecular formula. So it still has to have 6 carbons in the structure, but only 5 of them will be in the PC. So once when you decrease the PC size by 1, and then add a branch. So I'm going to add a branch, and branches have to be on the interior, cannot be on a terminal carbon. So here we go. So this is a 5-carbon PC branch, which is pentane. Okay, the branch N equals 1, so it is methyl. Okay, and we're going to keep doing this until we reproduce the same structure. So we'll come back to this. So now that I changed the PC side and add a branch, now because there's more interior carbons, I'm going to move the branch. So I'm going to keep my 5-carbon chain, and I'm going to move that branch 1 position to the right. Just be systematic. So in this case, I still have a 1-carbon branch methyl, 5-carbon parent chain, so I still have a methyl pentane. There's still another interior carbon, so I am going to move the branch again. So I'm going to keep my 5-carbon parent chain, and I'm going to add my branch 1 more position to the right. So once again, my parent chain is still 5 carbons, and I have a 1-carbon branch, so I still have a methyl pentane. So what I need to do is figure out these 3 methyl pentanes, are they unique to each other, or is there a reproduction? So to do this, we have to do the number designation. So getting used to doing this idea, I can see that this branch is much closer to the left side. So this is carbon 1, 2, 3, 4, 5. So this is definitely closer to the left side, so I know that this is 2-methyl. When I look at the next one, I can see it looks like that carbon is halfway between. So in this direction it's 3, but I'm going to look at it again in this direction. So that carbon, whether I look at it from the left or the right, it's on the 3rd carbon in the parent chain. So this is 3-methyl. Okay, so now when I'm taking a look at this next example, I notice that branch is much closer to the right-hand side. So I'm going to look at it from this direction. And my branch is on carbon 2. So this is 2-methylpentane. So here is the thing. I kept moving the interior branch until I have a reproduction of the structure. So this is not a new isomer. This is a repeat. So right now I have 3 isomers. This one is a repeat of the one up above. The molecule just flipped over. If I have to produce some more isomers, the next step here now would be that I've done everything I can do with a 5-carbon parent chain. So now I'm to the point where I need to change the parent size again. So now change the parent chain size. So now I'm going from 5, I've got to go down to 4. And remember, these are alkanes, so we can only use single bonds. And then we have to add branches. So here we go. I'm going to add a branch and add a branch because I have to have 6 total carbons in my structure. So my parent chain size is now 4 and it's single bond, so I know that is butane. I have a 1 carbon. Let me just change a color here. And I'll change this one. So my red carbon up above is a 1 carbon branch, so that's a methyl. And my green one down below is also a 1 carbon branch, so that's a methyl. So I know that out front I can put dimethyl. So I have my total number of carbons correct. So next step, keep building. Can I create some more? Move a branch. So here we go. I'm systematic as I can be. I keep my 4 carbon branch. I'm going to move my red one place to the right, but I'm only moving one thing at a time, and I keep the green one down below. So once again, when I take a look at this, I still have a 4 carbon parent chain, single bonds, so that is butane. The red is still a 1 carbon branch methyl. The green still only contains 1 carbon methyl, so I still have a dimethyl. All right, so now next step, move a branch. So I'm going to keep my 4 carbon chain just like I have. 4 carbon parent chain. I already moved that red one once, so I'm going to keep it in its spot. And now I'm going to move the green one. So when I take a look at this, I still have a 4 carbon parent chain, so it is still called butane. The red branch is still 1 carbon methyl. The green is still 1 branch methyl. So I have 2 methyl-methyl-butane, so I can shorten that to dimethyl. And there's no more interior carbon moves to make. So now my next job is, are all of these the exact same structure, or are there small differences? So we have to do the numbering. So take a look, number in this direction. Red branch is on carbon 2. The green one is also on carbon 2, left to right. Going back right to the left, red carbon or green carbon is on carbon 3, and the red carbon is also on carbon 3. So when you look at the way this is drawn, 2,2 is definitely the better one because it's the lower combination. So we have 2,2 dimethyl. When we look at this next one and we do our numbering, the green carbon, so first one we come to is on carbon 2. The red branch is on carbon 3. And when we look at this in the opposite direction, so renumber right to the left, the red branch is on carbon 2 and the green one is on carbon 3. So these are split in the middle, so our combination is 2, 3. So 2, 3 dimethyl butane. Our last example here, okay, is that now we have, when we number left to right, the branches are both on carbon 3, but if you look at them in the right back to the left, both of the branches are on parent chain carbon 2. So this is 2,2 dimethyl. So this is not a new or different isomer. We have a repeat structure. So this is a repeat structure, not a new isomer. That's okay. So once we hit our repeat structure, that means we need to make a different adjustment. So now, instead of changing the parent chain, but because we have two different branches, now we can try to change the size of the branch. So instead of having a 1 carbon branch, let's make it a 2 carbon branch. So here's my parent chain. It is still a 4 carbon parent chain. And now my branch has to be made up of 2 carbons. So this is what this looks like. So when I go to do this, I need to circle my longest parent chain possible. And that means how many carbons can I circle without crossing a carbon-to-carbon bond. So take a look at this. Look at how I can circle this. Here is my longest carbon-to-carbon parent chain. And even though I drew it with the reds looking initially like a branch, this is a 5 carbon branch, or 5 carbon parent chain, so that is pentane. And I have only 1 branch. So this gets a little sneaky, so you got to pay attention to the details. So this is the branch. This is not part of the parent chain. So this is a methyl pentane. And when I take a look at it, carbon 1, 2, 3, so it's on carbon 3, 1, 2, 3, it's on carbon 3. So that branch, it's a 3-methyl pentane. And when you look up above, we already had a 3 carbon or 3-methyl pentane. So this is not a new isomer. This is a repeat structure. It's just that the molecule is starting to bend and flex around. So in all, we were able to draw for this molecular formula 1, 2, 3, 4, 5. So we were able to draw 5 isomers. So C6H14, we were able to draw, what was it, 5 total, right? 5 isomers. So all these isomers, they have the same molecular formula. They are all C6H14, but their organic structure names are slightly different, so they are unique. So they're the same molecular, but they have different structural formulas.